Now let's calculate gravitational field strength due to a uniform hollow sphere. So if we talk about a hollow sphere, a uniform hollow sphere which is of mass m and radius r, then we can state as the sphere is a symmetric homogeneous geometry, then in its surrounding, if we talk about the gravitational field direction due to the mass, we can directly state by symmetry at every exterior point the gravitational field will be in radially inward direction. Or as if for outer point we can say that it appears that the gravitational field is directed toward the center of the sphere. By symmetry only we can state it. And in this situation we can state for outer points, whole of the mass of body appears that it is concentrated at center because the gravitational field strength is in radially inward direction. So here we can write that in surrounding at all points G vector exists in a radially inward direction. And here one more point we can say, for a uniform shell, we can assume that all of its mass is concentrated at its center. And mainly we are talking about outer points. Basically it is for outer points which are on surface or outside the surface. So if at any point P outside which is located at a distance x from the center, wish to find the gravitational field Gp will exist in inward direction, and we can simply state for outer points x, if it is more than r, gravitational field at point P can be written as gm by x square. We can directly use the result of a point mass, and similarly we can talk about surface points. So for surface points also we can state those points which are lying on the surface will experience a gravitational force Gs in inward direction if there is a point S on the surface. Then for x equal to r also we can consider gravitational field strength at the surface of a uniform hollow sphere can be given as gm by r square. We just substituted the value of x as r. But the same is not the case for interior points, because if we consider a point which is inside the sphere, we need to find out the gravitational field as on one side of the point's field at this point will be in this direction, and due to the particles of the shell on this side, gravitational field is in this direction. Let's continue on the next sheet to calculate the gravitational field strength at an interior point. So in case of the hollow sphere, if we consider an interior point P and we wish to find out the gravitational field at point P, then we consider small segments which are subtending small solid angles at point P on the two sides of P on the surface of the shell, which are located on the diametrically opposite points if this is the center. We can simply state, say, if this segment is located at a distance x1 and this segment is located at a distance x2 from point P, and say it is having a mass dm1 and this is having a mass dm2, then we can directly state in case of a spherical section, the surface area of the element will be directly proportional to the square of its distance from the point at which it is subtending a given angle. And here the solid angle or the angle subtended by both the elements at point P are equal, and the mass is obviously directly proportional to the surface area. So in this situation we can simply state this mass is proportional to square of x1 and this mass is proportional to square of x2. So here we can write dm1 is equals to some constant into x1 square and dm2 is a constant into x2 square. And similarly we can choose infinite number of segments on diametrically opposite points which are located corresponding to any point chosen at the interior zone, in the interior zone of the sphere. Now in this situation we can simply state the gravitational field at point P can be given as this Gp we can simply write as integration of dg1 minus dg2, where dg1 is the gravitational field due to dm1 in this direction and dg2 is the gravitational field due to dm2 in this direction, say it is dg2. So in this situation if we substitute the value of dg1 and dg2, you can see due to the point masses, if we use the result, it will be g dm1 by x1 square minus g dm2 by x2 square. As we already discussed that these elemental masses are directly proportional to the square of the distance of these elements from point P. If we substitute the values of dm1 and dm2 over here, these x1 square, x2 square gets cancelled out and the final result will be 0. So we can say at all interior points of a uniform shell, gravitational field inside is always equal to 0. If we just plot the variation curve of a gravitational field with the distance for a spherical shell, this can be directly given like if we plot the graph of g with x, and we can say from x equals to 0 to x equals to r, those are for interior points. This for x less than r, we can simply state the value of gravitational field strength due to the shell will be 0. At x equals to r, its value is given as gm by r square, which we have already calculated in the previous slide, and outside it is gm by x square. So we can say the curve drops in such a way that g is inversely proportional to x square. This is the curve which shows the variation of gravitational field with the distance from center of a spherical shell.